Let's see how acting with the ladder operators on an energy eigenstate ensures that the normalization condition remains satisfied. The concepts in this video are essential for understanding the quantum harmonic oscillator. In the previous video in the quantum mechanics playlist, I derived the relationships shown in blue and red. These are eigenvalue equations that involve the number operator. And capital N with a hat is used to denote the number operator. A and A dagger are collectively known as the ladder operators. This guy over here is also known as the lowering operator, and this one, A dagger, is known as the raising operator. The reason they've been given these names is because of this equation over here. If we act on an eigenstate, this over here is Dirac notation. This is a Ket vector labeled by lowercase n. And lowercase n is an eigenvalue of the number operator. These eigenstates are shared between the number operator and the Hamiltonian. So they are energy eigenstates, and they're also eigenstates of the number operator. So if we act with the number operator on one of these energy eigenstates, we get back the same energy eigenstate with a scalar out the front. And that scalar is lowercase n. It is the eigenvalue. But here's the thing, what we can do with these ladder operators. If we act with A on this eigenstate, it has the effect of decreasing the eigenvalue by 1. It turns n to n minus 1. And A dagger does the opposite. It turns n to n plus 1. It increases the value of the eigenvalue by 1. So from these equations, we can actually draw a very important conclusion. I'll write that conclusion underneath. We can see that acting with A on an eigenstate labeled by little n is the same as just giving us n minus 1. So the state n minus 1. And I'm using the Ket vectors over here. This is Dirac notation, and these are Kets. So this type of bracket situation that we've got going on over here, these guys are all Kets. And over here we have n, and here we have n minus 1. So acting with A on this eigenstate lowers the eigenvalue by 1. But we have to ensure normalization. That's what this video is about. So we have to introduce a coefficient. I'm going to call that coefficient C sub L. And L refers to lowering. This is the coefficient for the lowering operator. We can also write an analogous equation for the raising operator, A dagger. And A dagger is the Hermitian conjugate of A. So let's do that over here. So if we have A dagger acting on one of these energy eigenstates, which are also the eigenstates of the number operator, that's going to give us an increased version. We're going to have n plus 1 inside this Ket over here. So that's the label of this Ket. But we need to have a coefficient, exactly as we have a coefficient over here. I'm going to call that coefficient C sub R. So that's the coefficient for the raising operator. So have a look at this. A and A dagger, the ladder operators, are linked together by this Hermitian conjugate. If we take the Hermitian conjugate, or the Hermitian adjoint of A, that's going to give us A dagger. And if we take the Hermitian conjugate of A dagger, we're going to go back to A. That's exactly the same as the complex conjugate. When you take the complex conjugate of the complex conjugate, you get back to where you started. Because the complex conjugate takes I and turns it to minus I. And then when you do the complex conjugate again, minus I turns to plus I again. So you go from I to minus I to plus I. So let's have a look at what we've got over here. Here we have a Ket equation that tells us what the lowering operator does. And here we have a Ket equation that tells us what the raising operator does. But now what I want to do is I want to write the bra version of both of these equations. I'm going to do it next to them. So next to these guys, I'm going to write the bra versions. And I'll do that in a separate color so we can see very clearly that these are separate equations. So this left-hand side, if we take the Hermitian conjugate, is going to give the bra version of n. And then we're going to take A, we're going to turn that into A dagger. And this is going to be equal to the bra version of n minus 1. And we have to remember that there's this coefficient over here. But this coefficient, in general, could be complex. This could be a complex number. So we have to take the complex conjugate. Now the complex conjugate, if we generalize that to all of these bras and kets and operators, that turns into the Hermitian conjugate. So this Hermitian conjugate is a generalization of the idea of a complex conjugate. So when we're taking the Hermitian conjugate of this operator, we just use this dagger notation. So this A has turned to A dagger, this ket version of N has turned to a bra version of N, and over here, what do we have? We have this coefficient has been complex conjugated, and this N minus 1 in a ket version has turned to the bra version. Let's do the bra version of this equation as well. So I'll write down the bra version of this equation. So over here we're going to have the bra version of N, and then we're going to have this A dagger is going to turn to A. So we have A over here, and that's going to be equal to the bra version of N plus 1, and then we have to take the complex conjugate of this coefficient again. So we're going to have C sub R, and that's going to be the complex conjugate version. So now we have both the ket and the bra versions of these equations. So these equations up here are eigenvalue equations involving the number operator. And they tell us these relationships. They tell us that when we apply A to an energy eigenstate, it decreases the eigenvalue by 1. And when we apply A dagger to an eigenstate, it increases the eigenvalue by 1. So that is what we've written down here explicitly. And then we've taken both of these equations and we've taken the complex conjugate, or in more general terms, the Hermitian conjugate. And when we take the Hermitian conjugate, we turn the kets into bras, and we turn all of the operators to their Hermitian adjoint, or their Hermitian conjugate. So now what I want to do is I want to take the inner product of the ket versions with the bra versions. So let's do that. Let's take the inner product of the left-hand sides with the left-hand sides and the right-hand sides with the right-hand sides. So I'll write that underneath to make it very clear. So let's take this combination over here. We have the bra version of N times A dagger. And let's multiply that by this left-hand side over here. We have A, and then we have the eigenstate N. And this is the ket version. And now let's do the right-hand side of the equation. So that was the left-hand side, and now we have to do the right-hand side. So we have this combination over here. That is the bra version of N minus 1. And then we also have this complex conjugate version with an asterisk. That denotes the complex conjugate of Cl. And then let's have a look at this right-hand side over here. We have Cl and the ket version of N minus 1. Okay, so that's what we have over here. And let's see what we've actually discovered. What we've done is we've taken the inner product of the left-hand side with the left-hand side and the right-hand side with the right-hand side. Over here, you still have the original ket equation. And over here, what we have is the bra version. And we can see that this bra version is equal to this. So if we multiply this on the left-hand side, it's the same as multiplying this on the right-hand side. Here we have the bra version of N minus 1, and we also have the complex conjugated version. So now let's unpack what all this is telling us. This combination, A dagger A, is defined to be the number operator. So the number operator, if you write it in terms of the ladder operators, is A dagger A. So we can turn this left-hand side into a more convenient form. This is the same as the bra version times this number operator, and then we have the ket version. So we're actually sandwiching the number operator in between a bra and a ket. So that is what this left-hand side is equal to. So all I've done is I've made these brackets disappear, and I've joined A dagger and A into one single operator, and that operator is defined to be the number operator. That's the same number operator that we're dealing with up here. Okay, now let's have a look at the right-hand side of this equation. Whenever we have a complex conjugate times the number, that is the same as the absolute value squared. So what we have to do is we have to take the absolute value squared of Cl, and that's equivalent to this complex conjugate times itself. So that's going to be the same as the absolute value of Cl squared. So that's just from elementary complex numbers. Whenever you have a complex number times its complex conjugate, you're just going to get the magnitude square, the square magnitude of that complex number. Now, what's going on over here? We have the inner product of N minus 1, the bra version, and the ket version of N minus 1. And this is essentially the same thing. we're taking the inner product with itself. And here's a very important property of these energy eigenstates. The energy eigenstates are orthonormal. And because they're orthonormal, if we take the inner product of one of them with itself, that's going to give us 1. These guys are normalized. If this was different, if we had a different eigenstate over here, this inner product would be 0. And you can summarize that relationship using the Kronecker delta symbol. And we've used the Kronecker delta symbol in other videos in the quantum mechanics playlist. So this is going to turn into 1 because we have the same vector over here. This is the same label in the ket and the bra. So we're taking the inner product of an eigenstate with itself. And because we know it's normalized, this has to be equal to 1. So now, what about this side over here? This is actually the same eigenvalue equation that we have up here, except we haven't applied A or A dagger to the eigenstate. When you act with the number operator on one of its eigenstates, you just get the eigenvalue times that eigenstate. So what I can do is I'll move this to the left-hand side. If we have the absolute value squared of CL, that is actually equal to, I'll evaluate this, this is the same as little n multiplying the eigenstate. It's the same as the eigenvalue multiplying that state. So I can actually pull that eigenvalue out, and that's going to give me this. And have a look at this relationship over here. Here we have the bra version of n and the ket version of n. And if we take the inner product, again, with one of these eigenstates with themselves, that's going to give us 1. That comes from that orthonormality condition. And this n is all that's going to remain. So what we have is that the square magnitude of CL is equal to n. And what can we conclude from that? If the square magnitude is equal to n, we can take the square root. But we have to be very careful because this is a complex number. So what is that going to give us? CL is going to have to be equal to the square root of n times e to the I phi, where phi is some phase. But here's the very important thing. When we're interested in normalization, the phase doesn't actually matter. So this phase doesn't carry any physical significance to it. So we can choose phi to be whatever we want it to be. And for convenience, we're going to choose phi to be 0. And if phi is equal to 0, then e to the 0 is equal to 1, and then we're just going to be left with the square root of n. So we can summarize this entire relationship over here in a very succinct formula. When A acts on one of these eigenstates, it's the same as square root of n times the state n minus 1. So this is the ket equation that we had up here. And all I've done is I've found this coefficient. This coefficient is the coefficient that makes this work. It preserves the normalization condition. It makes sure the normalization condition remains satisfied. So I just want you to be very clear what I've done in this step over here. I had the absolute value squared. And because in general this could be a complex number, that means that this could lie anywhere on a circle in the complex plane. And the radius of that circle is the square root of n. And that's the same as n to the power of 1/2. Right? The square root, that's n to the power of 1/2, and that undoes this squared over here. So this can have any phase. But we're choosing this, by convention, to have a phase of 0. So phi is equal to 0 over here. So if you're unfamiliar with these complex exponentials, make sure you watch some of the earlier videos where I go into detail and talk about this polar form for complex numbers. Now, let's do the same thing for the red equation over here. Let's do this for A dagger, for the raising operator. So let's see what's going to happen. We have to take the inner product of this bra equation with this ket equation. And the reason we're doing that is so we can isolate this coefficient. Over here, when I took the inner product, that actually made this bra and this ket disappear. So I got rid of this ket, and I isolated this coefficient. That's why I'm taking the inner product with the bra version. So let's have a look at what we have. We have this guy over here. That's going to be on the left-hand side. So on the left-hand side, we're going to have the bra version of n, and then we'll have A, and then we're going to have a dagger, that's from up here, times the ket version of n. So that is the left-hand side of the equation. And I'm going to set this equal to the right-hand side of the equation. So I have to take this over here, the bra version of n plus 1, and then I need the complex conjugate of C sub r, and then finally this right-hand side over here. And this right-hand side has CR, and it has the ket version of n plus 1. So I've done the same thing as I did over here. I've taken the inner product of the left-hand side with the left-hand side and the right-hand side with the right-hand side. So this over here is still from the original ket equation, and this is the bra version of that left-hand side. And over here I have this is still from the original ket equation, and this is the right-hand side of the bra equation. So all I've done is I've changed this ket to a bra, and I've complex conjugated the coefficient. Now let's group these terms together and see what we get. On the left-hand side, we have something familiar. So over here we had a dagger a, and that is defined to be the number operator. But we don't have that combination over here. Here we have a dagger. We're not allowed to swap these guys over, because in quantum mechanics, operators are not necessarily commutative. So commutativity is not guaranteed to us. And in fact, a and a dagger are non-commutative. That's one of their key properties. And in a previous video, I derived this commutation relation. This is the commutation relation between a and a dagger. That's a and its Hermitian conjugate. So let's have a look at what this is actually telling us. In full, if we take this square bracket notation for the commutator and we write this out in full, we get a dagger minus a dagger a. And we know this is equal to 1, and I actually prove this in another video in the quantum mechanics playlist. So have a look at this relationship over here. What I can do is I can add this term to both sides. And that's equivalent to moving this term to the right-hand side. And that's going to give me this relationship. A dagger is equal to a dagger a plus 1. And this relationship is what I'm going to be using over here. This alternative relationship will come up in the next video in the quantum mechanics playlist. So let's implement this relationship. When we have a dagger, we can rewrite that as this equivalent expression. We can swap the order, and then we have to add 1. So let's write that underneath. We have this version of n, so that's the bra version of n. And then inside this sandwich of the bra and the ket, we have a dagger and a plus 1. And then let's finish this off with the ket. And now let's have a look at the right-hand side. We'll come back to the left-hand side in a second. So the right-hand side has got a similar form to this right-hand side over here. So what we're going to end up doing is we're multiplying a complex number by its complex conjugate, and that's the same as taking the mod squared, or the magnitude squared. So we're going to have c sub r all squared. So we're taking the magnitude and we're squaring that. Then we're going to take the inner product of the bra version of n plus 1 and the ket version of n plus 1. So here we have n plus 1, and here we also have n plus 1. And by orthonormality, we know that this has to be equal to 1, because all of these guys are normalized vectors. So now you can actually see why Dirac notation is so useful. We're calling this a ket and this a bra, and together they form a bra ket. So that is what happens when we take the inner product of these two guys. So now we've just isolated this coefficient squared, so we have the magnitude squared of the coefficient, and that's what we want to find. But what is going on this left-hand side? So now that we've swapped these guys over, we've turned a dagger to a dagger a, we've also had to add to that the commutator of these two guys. So if you swap them over, you have to take into account the commutator, and that's what this 1 is doing over here. So now what I'm going to do is I have this in a nice form. I have this in the form where I can write this as the number operator. This is equivalent to the number operator. And what I'm going to do is I'm going to split this sandwich up into 2 smaller sandwiches. I'll write that underneath. So here we have the square magnitude of CR. That is equal to this sandwich over here. I'm going to take this bra and this ket and apply it to this little combination over here. And that's going to be the same as a sandwich of the number operator. So that's what we have from this term. And now we need to take into account this 1 over here. Multiplying by 1 is the same as multiplying by the identity operator. So all we're going to have is a sandwich of the identity operator, and that's just the same as the inner product of n with itself. So we have the bra and the ket version, and together they form a bra ket, or a bracket. That is the beauty of Dirac notation. So this over here is again going to be equal to 1 by the orthonormality condition for these eigenstates of the Hamiltonian operator. And this combination over here is the same combination that we had over here. If you have the number operator acting on one of its eigenstates, it's going to be the same as the eigenstate multiplied by the eigenvalue. And that eigenvalue is little n. So I can write this as equivalent to, we're going to have n, and I can put the n inside, and then I'll move it out in a second. So here we have n, and then we have plus 1. So have a look at this combination. What I can do now is I can take this n, because it's just a scalar multiple, and I can move it outside. And that's going to give me this combination. We're going to have n times the inner product of these two guys plus 1. And we know this is equal to 1. So in the end, we have n plus 1. So this gives us n. This is just multiplying by 1. And that doesn't actually change this. And then we add 1. So we have n plus 1. The square magnitude is equal to n plus 1. But now we have to take the square root. We have to undo this square. And that's going to give us, I'll write this underneath. That's going to give us this combination. So C sub r is going to be equal to the square root of n plus 1. But we also have to take care of the fact that this is a complex number. So we're going to have e to the I phi. And this could actually be a different phi. This doesn't have to be the same phi over here. But we're going to choose this phi to be equal to 0. So we don't even have to worry about it. I can call this phi phi 2. And I can call this phi over here phi 1. And they could actually be different phis. And it would still give us the same magnitude. But I'm choosing that both phi 1 and both phi 2, both of these guys have to be equal to 0. And I'll write that explicitly underneath. So I'll write this over here. Actually, I'll do this guy over here. So here, this guy, phi 2, has to be equal to 0. And this guy over here, phi 1, also has to be equal to 0. Phi 1 also has to be equal to 0. So we're just choosing that as a useful convention. We could take these guys to be complex numbers with a non-zero phase. But the phase doesn't carry any physical significance. So now finally, I'm going to write this right-hand side over here in the same form that we have over here. And actually, I'll write it underneath over here so that we can do a final step at the bottom. So we have a dagger acting on n. That ends up giving us square root of n plus 1. And that is multiplying the ket n plus 1. So this relationship over here is analogous to this relationship. The only difference is that instead of a square root of n, we have a square root of n plus 1. And the reason we have that plus 1 is because of the non-commuting nature of a and a dagger. When we swap to the order of a and a dagger, we had to introduce the commutator of these two operators, which comes from this commutation relation. So these two are very important relationships. I'm going to put them in a big box because they're very, very important. We could actually have started with this and then proved other relationships from this one. But I've chosen to leave the coefficients ambiguous and then use some reasoning involving Dirac notation to get to these coefficients. So these coefficients ensure that the normalization condition remains satisfied when we act with a and a dagger onto these energy eigenstates. Now, I want to prove to you that this actually makes sense. I'm going to write a very important equation down here. So let's say we have the number operator, capital N, acting on an energy eigenstate. This is a ket. We can write this as a dagger, then a acting on this ket. So the number operator is the same as a dagger a. And we've used that fact in this equation over here. We've transformed a dagger a into n, and we've also used that fact over here when we transformed a dagger a into the number operator. So we know that this relationship holds. That is by definition. Now we can group this guy together. We can take a acting on this eigenstate, and we can group that together. And then we can use this formula over here to write that into an equivalent form. So we're still going to have a dagger on the outside, but this over here is going to turn into the square root of n times n minus 1. So that's what we're going to get. We're going to get the square root of n times the state n minus 1. Now that has just come from this blue equation over here. And this red equation we can then use to apply this a dagger onto n minus 1. So let's do that over here. I'm going to factor out this square root of n, and that's going to leave me with just this a dagger acting on the state. So I'm going to have a dagger acting on the state n minus 1. And this combination, we can use the red equation now. This combination is going to give me n plus 1 inside here. It's going to give me n plus 1 over here. So it's going to raise the value that is inside this label. But this label over here is not n, it is n minus 1. So if I raise n minus 1 by 1, that's just going to give me n. So what I'm going to end up with is, I'll write this underneath, I'm going to end up with root n still outside, and inside the brackets, I'm going to have the square root of n times the ket n. Now the reason this is not n plus 1 is because we started with n minus 1. So we're already below n, and this is helping us get back up to n. And now we have two factors of square root of n. And together, those two factors are going to multiply, and they're going to give n. So we're just going to have n acting on the eigenstate n. And you can see that this is the eigenvalue equation that we've been using throughout this video. When you act with the number operator on one of these energy eigenstates, it just gives you the energy eigenstate back, but you're multiplying by an eigenvalue. And that eigenvalue is lowercase n. So it actually works. Both of these equations work, and they preserve the normalization. We need to have these coefficients here to ensure that all of these vectors are normalized, because normalization allows us to calculate meaningful probabilities in the statistical interpretation of quantum mechanics. So hopefully all this Dirac notation made sense. If you're unfamiliar with this Dirac notation, there are other videos in the quantum mechanics playlist where we go through it. So just keep in mind, we were using kets and bras and a's and a daggers, and we used all of this algebraic manipulation to give us these coefficients. At the start of the video, I left these coefficients that help normalize these relationships over here, I left them unspecified. I left them to be determined. And we determined them to be these values over here. And then we verified that those values indeed do work. They give the correct eigenvalue equation for the number operator. We're going to be using these relationships in later videos in the quantum mechanics playlist. If you want to watch those videos, make sure you click over here.